Greetings and welcome, internet friends. This is a little bit early morning on a rainy day. One of my kids is still sleeping, so I might be a little bit quieter than normal. We're also doing a review activity of our Radicals and Complex Numbers chapter, which notice pulls from the Algebra 1 textbook, Chapter 9. It pulls from the Algebra 2 textbook, Chapter 3. And it pulls from the Algebra 2 textbook, Chapter 5. So we're pulling problems from a little bit all over the place. If you're doing this assignment on Big Ideas, it will unfortunately also show up in 3 different locations. So make sure you're on the hunt for those if need be. But here we go. We're going to jump right in. So simplify the expression. Hopefully you've already seen and done the other assignments from these units, so you might be familiar with some of these properties and whatnot, and so it's review, so hopefully you'll be somewhat familiar, and my explanations will be much briefer as a result. So let's see, I could break this up over top and bottom like so. I can square root of 45. Because this is a square root, I'm looking for the largest perfect square that goes into it. I believe 9 does, and it goes in 5 times. Square root of 7y, I'm going to have an issue with. I'm going to need to multiply by something to get this radical out of the denominator. And we always multiply by 1, or more specifically, some version of 1 that is going to change the way that this looks. And so we had this trick of, if I multiply by rad 7 over rad 7, I'm going to be able to get the radicals to cancel out. And so here I would have times the square root of 7y kind of still up top, and root 7y times root 7y is plain old 7y. And the videos from that unit explain like 3 different ways as to how that happens. But essentially it just cancels out the radical for square roots when you multiply it by itself. Let's see, so square root of 9 up top is 3. Square root of 5 times 7 is 35 with a y still on the inside over 7y. I can't cancel out these because there's no common factor. I'm not allowed to cancel out these because one's in a radical and one is not. And same thing goes for the y's. So that is done in that form. Now this problem here, once again, the problem is this radical in the denominator. I can't simply multiply by this because it would get rid of that one, but then it would redistribute another radical there. And so what we did was multiply by what was called the conjugate. And so where just the middle term is different. So notice all I've taken is that plus sign, made it a minus sign. I have to remember that this behaves... this fraction bar behaves like a grouping symbol, so this is like it's in parentheses, so I'd have to distribute here. So 8 rad 6 minus 16 over, and then these two things match the difference of squares pattern. So I'm going to have a squared minus b squared, and I've explained that a lot, so go check it out if you need to, but a squared minus b squared from the difference of squares pattern. So I'll have 8 rad 6, not 16. Oh dear, oh dear. My wires are getting in the way of my undo button. Minus 16 over rad 6 squared becomes 6, 2 squared becomes 4, and 6 minus 4 is 2. Okay. Now, we actually haven't had a lot of problems like this, but it turns out this 2 can be reduced with this 8. But if I'm going to reduce it with the 8, because there are 2 separate terms here, I'd have to reduce it with both of those terms at the same time. And so both of the parts that are not in radicals can be reduced by 2. 2 goes into 2 once, into 8 4 times, and into 16 8 times. So final answer, 4 rad 6 minus 8 all over 1, which I don't even have to write. And so this is the fully reduced simplified answer. Over here, we'll do some distribution. I'm tempted to reduce that 18 now. It'd be what, 9 and 2, and then 2. No, I'll just multiply it. 6 times 18, and yes, I did reach for a calculator for that. Square root of 108, and yeah, I'm distributing. Plus 6 times 8 is, guys, why do I always do this to myself? How is this possible? 56. What am I doing? 48. Now let's see what the largest perfect square is that goes into both of those. 4 does, I believe 9 does, but I think even better is 36 does. And I'm guessing it fits in 3 times? Yeah. Plus, largest perfect square that goes into this, well, 2 goes into 6 and 4. Oh, shoot. I think I can get a 16. Yeah, 16 goes into this this many times. All right, and so yeah, just reach for a calculator, try your division of your perfect squares. Square root of 36 is 6 rad 3, plus square root of 16 is 4 rad 3. And hey, these happen to be like radicals, and I combine them similar to how we did like terms with variables. I'm just going to take the coefficient parts and add them together. 6 plus 4 is 10, rad 3's final answer. Okay. All right, we're cruising. Oh, then we had I, which is, by the way, equal to the square root of negative 1. So it's our imaginary unit is what we've got. So let's see. I'm still trying to figure out the adjustment on my laptop wires. I feel like I wasn't having this problem yesterday. Let's see. Maybe I can put my feet up. That's a little bit better. Right. 5 times negative 4 is negative 20. 5 times 7i is plus 35i. 6i times negative 4 is negative 24i. And 6i times 7i is plus 42i squared. And now, let's see, we can combine some like terms. So these i's can come together. So I'll have a negative 20 plus, let's see, 35 minus 20 would be 15 minus 4 is 11i, I believe. Yep. Plus 42. And now I squared, if I is equal to the square root of negative 1, and then I square that value, I get plain old negative 1. Yeah, check that out. And then I can combine some like terms again. Negative 20 and negative 42 is going to combine to be negative 62 plus 11i. All right, 7x squared plus 21. Solve. Subtract 21 from both sides. 7x squared equals negative 21. Oh, this technically... Oh, we could have tried solving by factoring, but we're gonna use roots to solve here, and we'll do some exploration in future the future chapter regarding that as well. Divide both sides by 7, and x squared equals negative 3. Now to undo this square root, I can root both sides, plus or minus, don't forget it, and I get x equals plus or minus. Oh, that negative could be broken up into the square root of negative 1 times the square root of 3, and square root of negative 1 is I, and so x equals plus or minus I rad 3. So technically 2 answers at play there. All right, then we learned how to do rational exponents, and it turned out that the denominator of a exponent can be written as the index of a radical. And so this 3 becomes this 3 in the radical. So the cubed root of negative 27. Now this negative 2 is still in the exponent, and I actually can have it inside the radical, or I can have it outside the radical. That those operations are commutative? No. Nope, that's not actually one of those properties. But it's whichever order you want to do that in is fine. Cubed root of negative 27, you might be like, cubed root of a negative, that's going to be imaginary. Except odd. roots will give you one answer and can work with negatives. So cubed root of negative 27 is negative 3. Negative exponent property, we would move it downstairs in a fraction. So this is now 1 over negative 3 all squared. So notice the exponent becomes positive. And 1 over negative 3 all squared is 1/9. Woo! Did it. And there are, like I said, multiple ways of writing that, multiple paths to doing this problem. As long as you obey the laws of math, you will get there. Let's see. Let's solve for this. So I could divide both sides by 7. I feel like I should know this one. But I also should know 7 times 8, shouldn't I? 189 divided by 7 is 27. There we go. And cubed root both sides this time in order to get rid of the cube, right? Those are inverse operations of one another. Also, notice this time I'm not plus or minusing. A moment ago, when I root-rooted both sides, I plus or minused and didn't forget it. If I have an even index, I need to do the plus or minus when solving. If I have an odd index, I do not. And so I get x equals 3. Final answer. Just one root for an odd index. Okay, simplify the expression. 4th root times 4th root. Let's combine those. 32 times 8 is 256. What's the largest perfect fourth? 64 is, I think? Yes. So yeah, the 4th root of 64 times the 4th root of 4, because 256 divided by that is that. And so the list of perfect fourths, 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is, wait a minute. No. Wait a minute. Is 64 a perfect fourth? Or am I thinking of 4 cubed? I'm thinking of 4 cubed, guys. Oh dear. 2 to the 4th is 16. But I'm going to get multiple of those in there. What's 4 to the 4th? Oh, 256. Now, this was a true statement. It just wasn't helpful for us. So yeah, 116, 81, and 4 to the 4th was 256. So that was a perfect fourth. This was true. It just wasn't helpful. The answer was just 4. Boom. All right. And we taught you how to access that on a calculator using kind of the nth root feature or the xth root feature, whatever you want to call that. Let's see. We could combine like radicals if they were like. Let's first try to simplify the square root of 48. Actually, I did that one already earlier. 16 is the largest perfect square that goes into it. Square root of 16 is 4. Let's see. And 2 times 4 is 8. 8 rad 3 minus rad 3. Now, the coefficient, so to speak, on this one is 1. Those are like radicals. They have the same index and the same radicand. And so I can just subtract 8 and 1 and get 7 rad 3s. Okay, we're cruising. We're almost on the last boss fight problem. I've been excited about that this whole time. Okay, assume all variables are positive. On the test, I'm going to also have that be the case, so you don't have to worry about the weird absolute value rule in that case. Now, square root, the index is 2. What's the largest exponent that's divisible by 2? Well, that would be 4, z to the 4th, and I would have a z to the 1st left over. And then I'm subtracting this, so I've got, what, z squared? Square root of 40, largest square root that goes into 40 is 4 and 10. 4, yeah. So 4, I've got a 10 and a z. Okay, so square root of z to the 4th is z squared, and because I'm assuming positive, I don't need the absolute values to show up, times the square root of 10z, as the two irreducible parts can just be written in a single radical, Square root of 4 is 2. Oh man, my 2's and z's always looking the same. 2z squared still there, and times 10 10z. And now I can just combine these. These are like radicals. So here's 1z squared root 10z minus 2z squared root 10z. And so I'm going to have negative 1 z squared root 10z. So yeah, the 1 and the negative 2 kind of behave like coefficients. And here we go. This is what I was waiting for. Yeah! Solving radical equations. The way you do this is get one of the radicals by itself. Most of the problems only have a single radical. I chose the most difficult to go over with you. And then apply the exponent that will undo that index. So this is a square root, so I'm going to square both sides. Now the left-hand side here is easy peasy. But the right-hand side is going to require me to apply the the a plus or minus b all squared pattern, right? The square of a binomial, which is equal to a squared plus or minus 2ab plus b squared. And this one has a minus sign, and so I'd be applying the minus version of the pattern. In this case, a is... I'll just write it over here. The entire root 5x minus 1, and b is the 1. Okay, so a minus b all squared. Let's plug this in. So a squared minus 2ab plus b squared. Here we go. A is this squared minus 2 times a again times b plus b squared. So I've plugged it in proper. 4z minus 4 equals, this whole square root and square cancel out. That's helpful. 5x minus 1. Here I've got minus 2 rad 5x minus 1, because the negative 2 times 1 was just negative 2. And I've got plus 1. Now notice, this is better than I started. This had 2 radicals, and this equation only has 1. And so now I'm going to treat this like I do some of the earlier problems. I almost said easier, but they're not necessarily... They are easier, but that doesn't necessarily mean easy. So I'm going to get this radical by itself. Okay? So let's see. Let's do a whole bunch of moves simultaneously. How did I get x's? How did I get z's? Let's make these x's. I was on a roll with writing z's in the earlier problem, apparently. All right, let's subtract 5x from both sides. Let's add 1 to both sides. Let's subtract 1 from both sides. Notice I'm just putting all of these under the common. You guys are good at those algebra steps, and since for adding and subtracting, let's just do all of it in one go. So 4x minus 5x is negative x. Negative 4 plus 1 minus 1 is still going to be negative 4 equals negative 2 root 5x minus 1. Now, I showed you this trick in one of my videos where, yes, I'm allowed to divide both sides by negative 2. But the problem is, and it's not a problem, it's just inconvenient, I'm going to create a fraction here, right? This will reduce okay, but I'm going to end up having to square both sides and deal with fractions. And I feel like avoiding that. And since squaring can be distributed over multiplication, that's exactly what I'm going to do. So let's square both sides in their current state. So, hey, look at this. I'm using the pattern again. Oh, dear, dear, dear. You know what I'm going to do? I've got a bunch of negatives floating around. Let's opposite everybody. Otherwise, we're going to start getting sign errors. And this is a single term, and so oppositing that one sign is sufficient. So now let's square both sides. Hopefully that'll avoid us screwing up. So here I'll have x squared plus, and using this pattern, 2 x times 4. Ooh, I would have messed that up. Good thing I didn't. I almost used a shortcut on that, and I would have been wrong. Okay. Equals 2 squared is 4, and root 5x minus 1 all squared becomes 5x minus 1. Now, one of the potentially tricky parts about squaring both of these is that this is going to be in parentheses. So you've got to play it safe. Play it safe. All right, here we go. X squared plus 8x, because 2 times 4 is 8, plus 16. Let me make a prettier plus sign for you. We might as well do our job well. We're 20 minutes in. We're almost there. Distribute here. 4 times 5x is 20x minus 4. Now, I've got a quadratic. I've gotten rid of all my radicals, finally. And at this point, we only know one way to solve for quadratics, which is to set it equal to 0, factor, and solve using the zero product property. So let's get this equal to 0. X squared minus 12x plus 20 equals 0. And now I'm going to factor this, which fortunately the leading coefficient's 1, so I don't even have to do AC method. I can just find the factors of 20. So 1 and 20, 2 and 10, 4 and 5. And by the way, this list of factors, when you're doing the Google form test later, you can avoid writing this list of factors. But yeah, try to write, all of your other work, or at least the yellow parts. Right? If you write all of your yellow lines, I'll be able to interpret what you did in between and give you partial credit. You technically could go through and try to write the work steps, the orange parts, but I'm trying to save you some time, but I guess there is the risk that you could make an error as you're typing in Equatio on that test. And actually, that reminds me, I have sent out a video tutorial on how to use Equatio. I might make one myself just to help all y'all out. So let's see, x with a, which of these add to be 12? The 2 and 10. So x with a 2, x with a 10 equals 0. And they have the same sign because they multiply to be positive and they add to be negative, so minus minus. And then 0 product, x minus 2 equals 0, x minus 10 equals 0. Therefore, x equals 2 and x equals 10. Now, all of this work done, and I don't know if either of these are legitimate answers. I've got to do a check, and this is a mandatory check, because it's possible, even though I assume I didn't make a mistake besides this one, it's possible that we are wrong, that some of these solutions can be extraneous. And so I'm going to plug in square root of 4 times x minus 4. Is that equal to the square root of 5 times x minus 1 on the outside? I've got to plug in both of those quote-unquote answers and do a check twice. So one of my possible answers was 2. That was this one. That's not a negative 2, by the way. So one of my possible answers is 2. So I'm going to plug it in everywhere I saw an x in the original problem. I'm not allowed to plug it in earlier because then I'm only checking earlier, from that point on whether or not it was an answer. I need to check it all the way back at the beginning. And so 4 times 2 is 8 minus 4. And yeah, you'll need to do this step in Equatio as well. I'm sorry, guys. It's not the best, but it'll work. It'll work. Actually, I don't know. I've gotten pretty fast with Equatio now that I think about it. Square root of 4 is 2 equals square root of 9 is 3 minus 1. And that works out. So what does that tell me? That tells me that my answer 2, x equals 2, is legitimate. So this problem has at least one solution. Let's see. The other one is 10. So 10 here, 10 there. So square root of 4 times 10 is 40 minus 4. Is that equal to the square root of 50 minus 1 on the outside? Is that equal to square root of 36? 49 minus 1, square root of 36 is 6. Square root of 49 is 7 minus 1, and that's true! Hey! And so this problem had 2 solutions, and it took quite a while. All right, yeah, yep. This is why I call this a boss fight, guys. It uses so many of our skills. It uses special products. It uses factoring, right? It uses all of our new radical work. It is a beast trying to get this problem done. But anyways, I believe in y'all. You can do this. Be in touch. Email me questions if you have them. Have a good day. Mr. Waddy out.